Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. Today we are going to talk about regularization in machine learning and deep learning in a unified way. What this means is that we're going to talk about traditional machine learning methods such as linear regression, polynomial regression. Then we go to support vector machines, and at the end we're going to talk about deep learning models. And overall, the goal is to show you the importance of regularization and how it can actually be done through a little bit of math and also implementation using scikit-learn and Keras. If you find this video helpful, please don't forget to like and subscribe. So what is regularization? In simple terms, the goal of regularization is to constrain a machine learning model to make it simpler and make sure that it generalizes better. So what does it mean to generalize better? Remember that in machine learning, we have typically two datasets, a training dataset and a testing dataset. It is relatively easy to perform well on the training data because we already have both the input data and the corresponding outputs or labels. But what really matters is that how well this model that we train will perform on some test data or unseen examples. And that's what we call as generalization. So to understand this whole idea, let's look at a very simple model, which is linear regression. You can see that here the hypothesis H is theta 0 plus theta 1 x. Theta 0 is the intercept, and theta 1 is the slope of this line. And the goal here is to find these two parameters using some training data. As we know, for finding these parameters, we have to set up an optimization problem. And we can see here that the typical cost function or loss function for regression problems is to subtract the actual values from predictions, and this is what the model gives us, this h of xi. And remember that I'm using this subscript to show that these theta are the unknown parameters and what we are optimizing with respect to. And the goal is that to find this, what we call it as the squared error, and then you can take the average or the summation of these error terms, and we want to minimize it with respect to theta, right? So this is the typical optimization problem for linear regression. So now let's look at this data set that we have here. So to make it simpler here, we have this x as a single input variable. And you can see here on the x-axis, we assume that we have GDP per capita. And the goal is to find a regression model and understand whether life satisfaction in different countries is correlated with GDP, right? So we assume that countries that are richer, people should be happier. And I intentionally here, I have two data points that if you can see here on the top of this figure, that are very different than the other data points. So I intentionally use this example to show you the importance of regularization. Let's start with the simple linear regression as we saw earlier when we solved the minimization problem. And if we do that, we can see that this red line is the solution. And here we also have the intercept theta 0 and the slope theta 1, right? So this shows that this theta 1, which is 0.07, is the slope of this red line, which shows how life satisfaction and GDP are related to each other. But if you look at the countries that they have GDP above 50, you can see that this line kind of like is above those data points, right? And the fact that the reason that this happens is because those two data points that we have on the very top of this figure, they are pulling this line towards higher slopes, right? And so what this means is that now this function is changing rapidly, mainly because of these two data points that they are far. And this can be, simply due to some errors or some outliers. And this is not something very desirable in this case. So what we're trying to do here is that how we can reduce this sensitivity to these two data points that are different from others. This is exactly where regularization comes into play. So you can see that here, this red line, as before, is what happens when we don't have any regularization. And the green line is now the case that we used regularization. And as you can see, now this green line, it looks like that is doing much better job in terms of capturing the trends that we have in this data set. And you can see that the slope now is about half of what it used to be. But how we found this solution? So that's what we want to talk about in the next slide. Okay, so now let's revisit the optimization problem that we had earlier. So the blue part is exactly the part that we measure the differences between predicted and actual values. Now you can see that we have this second part, which I show here in this green color, which is alpha, which is a constant, right? Just a fixed number, times the sum of the squares of these two parameters. So in other terms, what we're doing here is that we are adding the norm or length of this vector theta that contains parameters to our optimization problem. And now this overall optimization problem, on one hand, tries to minimize the error between predictions and actual values, and on the other hand, aims to reduce the norm or length of this vector, right? And what happens is that, think about it this way: when theta 1, especially here in this simple case, is close to 0, this means that now the slope of the line that we find is smaller and closer to 0, which means that doesn't change as fast as the cases where theta 1 is or takes higher values. And on the other hand, you can see here that we have these, what we call it as regularization parameter alpha, that if we set this equal to 0, this means that we completely ignore the second term, the green term here. And in this case, we don't have regularization. That's the standard linear regression. And then when alpha is a positive number, then in that case, we are basically adding this regularization to this machine learning model that we have. In this case, for example, I use alpha equals 10 to the power 4 to find this solution that you can see here. And something that you want to take into consideration here is that when alpha equals to 0, we don't have any regularization. And if we choose alpha too large, like what you can see here, like 10 to the power of 5, what happens is that then these parameters theta 0 and theta 1 should be very close to 0. Otherwise, they will be the dominant term in the optimization problem, and that's not ideal because we want to minimize the entire term, right? So as you can see here, when I chose alpha too large, which here is 10 to the power of 5, and this depends on your problem, you can see that now this green line is a sort of like a horizontal line, like, so it predicts the same value for every input, and that's basically something that is completely useless. And that's why you have to always find appropriate values for this alpha, and that's one of the key challenges of using regularization. So now we intuitively understand how regularization works for a simple linear regression model, but let's look at a little bit of mathematical analysis here to get a little bit better understanding. So what we do here, if we remember our hypothesis, or this function h was theta 0 plus theta 1x, and I set theta 0 equals to 0. So this what means is that now we want to find a line that goes through the origin, and theta 1 is the slope, which is the only parameter that we have. And I do this because now we can solve this minimization problem using simple calculus, which means that if we write down the function and take the derivative and set it equal to 0, we can find the solution. So in line 1, you can see that this is the optimization problem that we have. In line 2, we take the derivative, and here you can, for example, use the chain rule. set yi minus theta 1 xi, which is in the parentheses to, let's say, call it z. So the derivative of z squared, it's 2 times z. And then you have to take the derivative of z with respect to theta 1. That's where we get this negative xi in line 2. And then we have this quadratic term theta 1 squared, which the derivative would be 2 times theta 1. And then we have that constant alpha. And then we set this equal to 0. In line 3, what we do is we divide all the terms by 2, which is a constant. We can do that for both sides. And then in line 4, we are going to expand the first summation with the parentheses. So that's where we get this negative summation of yixi plus, because we have two negative signs, theta 1 summation of xi squared. And then we can factor theta 1, and we take everything else that doesn't have theta 1 to the other side of equality. And this allows us to simply divide both sides by the constant that is multiplied by theta 1 to find the final solution. And here is the simplified result that you can see that theta 1 is the summation of xi yi's over summation of xi squared plus alpha. So what does this mean? What this means is that when we increase alpha, the regularization parameter, then theta 1 should decrease, right? So in other terms, we can say that the strength of regularization is proportional to this parameter alpha. And that's like the key thing to remember here. So meaning that alpha 0 is no regularization. Alpha, as it increases, we are having more regularization. And as you can see, this is what I have here from scikit-learn when you look at the linear model. And this is also known as regression, right? So this type of regularization term that we added with the sum of the squares or the L2 norm, that's called regression. And this is exactly the optimization problem that we just talked about, except the fact that in scikit-learn they call this W, which again is a vector, and instead of calling it theta. But overall is exactly what we had before. So here the story is that if you want to understand regularization, you need to look at the optimization problem and how this regularization term has been added to the original objective function for that machine learning model. So far, we have a basic understanding of regularization, but in fact, regularization is very helpful to avoid overfitting. So the first question is, what is overfitting? Overfitting happens when a machine learning model performs well on the training data. So as if you remember, we said that that's usually like the easier part, but doesn't perform well or generalize well on the testing data set. And what basically one of the main underlying reasons for this is that when the machine learning model that we use is too complex. So here I'm looking at exactly the same problem that we had before. And instead of using linear regression, now I want to use polynomial regression, meaning that I'm using polynomial features. And for some reason here, I decided to use polynomial features of degree 5 to just make sure that I can capture any nonlinearity that I have in my problem. And this is defined using this pipeline. And I actually have a video to understand how pipeline works. But the idea is that you can combine several transformers and estimator, meaning the regressor or a classifier. So the first two parts here in this pipeline are for polynomial features and making sure that the features are standardized. And then the last one is basically that regression with this alpha parameter that you can see here, which is 100 or 10 to the power of 2. So here, as you can see in these two results that we have, when we don't use any regularization, what happens is that this model tries to very much memorize these training data points. And as you can see, especially when we have GDP greater than 50, this red function that we have does not do well at all in terms of capturing the trend or the structure in the data, right? And this happens because this model is fit too well to the training data, but it doesn't generalize well. So that's exactly the idea behind overfitting. On the other hand, you can see that when we use regularization using this regression, we found a nonlinear function, the green one that you can see in the dot that it shows using this dotted function. And obviously we can see that, even though it's nonlinear, but it's very smooth, and it's very more likely to capture the trend of data and perform well on the testing data compared to the case when we don't use regularization. So here, one important thing to remember is that the main purpose of regularization is to avoid overfitting, and overfitting becomes critical when you have a model that is too complex for the data that you have. So it's always relative to the data that you have, and that's how we can decide about the complexity of model and regularization. Another thing to keep in mind is that there are different forms of regularization. Previously, we talked about the case where the regularization term was basically the sum of the squares of the parameters, but here you can see that we have the sum of the absolute values. In fact, the main thing that you have to take into account here is that the regularization term should be always positive, because otherwise, because you're solving a minimization problem, that's very problematic, right? And obviously, the sum of the absolute values are positive. And also this is called what is known as the L1 norm, right? So before we had L2 norm, and here is called L1 norm, and you can see it with that 1, which is the subscript here. So for comparison purposes, I have here show you the result when we don't have any regularization with the polynomial features of degree 5. When we have regularization using the regression, which was the previous slide, and then we have regularization using Lasso. So obviously these two are different, and in practice you may want to try both and see which one works better. A main advantage of using Lasso is that it is more likely to find parameters that are exactly equal to 0, right? So that's why they use Lasso for also feature extraction. Okay, so now let's move on to classification. And in this case, we are looking at support vector machines that are very useful when you have relatively small data sets. And they're also easy to interpret. So the idea, as you can see here, is that let's say we have two classes, the red squares and the blue circles, and you want to find a hyperplane, or in this case, simply a line that separates the two classes. And the idea is that you want this line or this hyperplane to have maximum margin from both sides. That's why support vector machines are called margin-based classifiers. I'm not going to go through all the details here because I have another video that I discuss support vector machines, but my focus here is on the regularization part. So this is the documentation from scikit-learn, which shows you how this optimization works. So again, we have a minimization problem. And the first term, which is this W transpose W, which is exactly the norm of W to the power of 2. If you're familiar with linear algebra, that's the part that we want to maximize the margin. If we look at here, the margin is 2 over norm of W. So maximizing the margin means we want to minimize the length of W. So that part is always there. But the part that is about regularization is this term C times the sum of CIs. And CIs here are basically like, shows you the violations from this classification rule, right? So you can see that there's one red square, which is on the wrong side of this line. And that shows you the CI, like how much we are, on the wrong side, right? And obviously the goal is to minimize the entire term, but the fact that matters here is that the balance between the two terms that we have in this optimization problem is again controlled by this regularization parameter, which is called C, which is a constant similar to alpha. But what I want to here explain is that whether C is proportional or inversely proportional to the amount of regularization. So if you look at what we have here, because C is multiplied by the errors, so this means that if C is very close to 0, then we don't really put much emphasis on how much error we have. But when C is a large number, even a small amount of error can cause problems for this minimization problem, right? Because then we are not really reducing this second term that we have here. And for this reason, if we look at the documentation page, it says that the strength of regularization is inversely proportional to C. And we can show you this exactly here with this simple example. So here, again, we are using support vector machines. And the goal is to separate these two classes. Here we are also using polynomial features to be able to also find nonlinear decision boundaries. And what really matters here is that on the left, when C is equal to 100, we can see that we're almost perfectly classify the two classes. And for that reason, decision boundary has to have more abrupt changes. So it's not very smooth. But then when we reduce the value of C, then we allow for more misclassifications. Means that this decision boundary shouldn't be very rigorous as before. And in this case, you can see on the right side that this decision boundary is now way more smooth, but we are making more mistakes in terms of missing a few red circles and these red squares and blue circles. But this might be actually helpful when you have data that is noisy, or in some cases that it might be very difficult to actually classify correctly the data points that are close to decision boundary. So that's the idea behind regularization in support vector machines. And as you can see, is a little bit different from linear regression in terms of the, increasing the value of C here means we are having less regularization. So in some ways, it's the opposite side. But now you understand how this works. In this slide, we're going to talk about the implementation of how I could get those results for support vector machines. You can skip these two slides that we have here. But if you're interested, first you need to create a two-dimensional grid. And we can do this using NumPy. We use NumPy.linspace to create, let's say here, 4 data points from -1 to 1. That's what you can see here, and then 3 data points from -1 to 1 for the y-axis. And then after that, we can use this numpy.meshGrid, which gives you these two-dimensional arrays where we have these sort of like 4 values for x and 3 values for y, and they are replicated as many times as needed. And then using this np.c, we can concatenate these two-dimensional arrays, and this gives us this two-dimensional grid that you see here. So this means that now I can train a support vector machines and use this two-dimensional grid to figure out which class each data point belongs to. So finally, for the main implementation part, you can see here we are using the make moons data set. We're using pipeline, polynomial features, and also support vector machines. We are again using pipeline to combine these transformers and estimators, which is here the estimator is this support vector machine. Here you can see that we put the regularization parameter C to be 100 and use .fit to train this model. And finally, you can see here this is the part that we are using the approach that we just discussed to find a two-dimensional grid. And after finding that, we just need to make predictions. So these are basically our test data points. And finally, we are using a contour plot to find this nice figure that you can see in this case here. So this explains you the main steps if you want to reproduce these figures. Finally, let's talk about regularization for deep learning models. Here we are looking again at the optimization problem, which looks very much like linear regression, except the fact that when you have neural networks, this h of x or this prediction model is more complicated because it's not just a simple linear combination of inputs, and in fact is a nested function or composite function, meaning that you find a linear combination of input features and then you take it to the next, like let's say hidden layer. You can apply some nonlinear function and you just continue this process until you get to your output layer. And anyways, what you can see here, we have this standard sort of like part of the cost function that measures the accuracy of predicted values. And similar to the linear regression, you can always add this alpha times here like this L2 norm of the parameters. And remember, this theta here is not just theta 0 and theta 1, and this is in fact the parameters, or in deep learning we usually call these weights. So these are the weights that we have for all these layers. And to show you how this works, here I create a synthetic data or simulated data where we have these input features x1 to x200, and we find this summation plus some constant and some Gaussian noise that we add. And the goal is that now we have this single layer neural network where the input has 200 neurons, and then in the hidden layer we have 2 neurons, and in the output layer we have 1 neuron. And what we want to see is the impact of adding this regularization term, which is shown in green. On the left side, we see the case where we don't use any regularization. And what happens here is that as we have here on the x-axis the number of epochs, we can see that the gap between the loss on the training data and the validation, or you can think of this now as the testing data, is increasing, right? So this is one sign of overfitting, meaning that we want these to be too close, but they're getting actually farther from each other. But on the right side, you can see that we can simply in Keras add this regularization term, which is this kernel regularizer, and you can add L1 or L2. Remember, this shows you if whether you want to have the sum of the square or the sum of the absolute values. And then inside the parentheses, that's where you add that regularization parameter or constant, right? Which we call it, here alpha. And you can see that here by setting appropriate values for this regularization parameter, now the situation is much better in a sense that the value of the loss function on the training data and validation data are closer to each other. And so that's the basic idea behind regularization, whether you want to use it for traditional machine learning models or deep neural networks, where the goal is to make sure that the machine learning model performs well on the test data, or what we call it at generalize well. And the idea is that we want to constrain the model to make sure that the model is not just fitting to the training data, and it actually can learn the underlying structure and patterns in the data. I hope you found this video useful. Thanks for watching.